today we have the pleasure to have Marcello Dalmonte coming from Trieste. Marcello got his PhD in 2011 with Elisa Ercolesi. Was that in Bologna? Yeah, that was in Bologna, working on 1D quantum systems. And then he moved to Innsbruck to work with Peter Zoller for 5 years, and there he extended his broad view on quantum many-body problem and entanglement. And in 2016 he moved to ICTP as a Boltzmann Fellow, and 1 year later he became a staff member there, and he's developing a very broad activity on quantum many-body problem and related to entanglement and other concepts borrowed from various fields. So today I think he's going to give us an overview. Thank you very much, Marcello, for coming here.
Thanks a lot, Frederic. Thanks everybody for coming. Okay, so today's topic is problematic from the very beginning, because you can see from the title there is a word that scientists are not very accustomed to, magic. Okay? So what I would like to tell you today is a bit how we learn how to handle this concept. That is something which comes originally from the field of quantum computing, quantum information. And in particular, what I will be interested in is to translate and utilize this concept in the context of many-body systems. Before starting, let me emphasize that this is work mostly done by my younger collaborators, in particular Martina, Poetry, Emanuele, and Pedro are the guys responsible for the results I will show you today. So what is the question that we want to address? Okay? So suppose that one day somebody comes to us and has a correctly working quantum computer, something which has error correction built in, like our classical machines. Okay? Can we quantify within this context how difficult it is to realize a certain state of matter? Okay? So this is the concept that we are interested in. And of course, we don't just want to have a random state of matter, we want something which is interesting. That from the point of view of statistical physics can be like a critical system or a gauge theory or some examples, you name it. Okay? So that's the question we want to address. And I will argue that magic is important, and to some extent is fundamental to answer this question. And the way I will do it, I will first introduce it, how we quantify complexity of quantum states, then I will show you how nowadays we can actually compute these things. This magic has a long history. It's actually something that the word magic first appeared in a paper by Kitaev in 2005, but until a few years ago it didn't really enter many-body. I will show you why. And nowadays I show you how we can compute it, how we can understand the relation between magic and another source of complexity that we know very well, which is entanglement. And towards the end I will show you examples taken from quantum statistical physics that underline the fact that magic can be important to diagnose certain phases of matter. Okay? So, first thing that I always thought is that okay, entanglement is the thing that makes quantum object complex, because we cannot separate it. Okay? It's a lack of separability. Isn't this enough? And in my very naive many-body theorist viewpoint, I always thought this is enough. But then I started noticing that there were many papers that were actually studying many-body systems at large scale with a lot of entanglement, generic, non-integrable, non-Gaussian. And this is just an example by Matthew Fisher and co-workers. The idea is that in these systems what they have is evolutions which are not generic, but where gates, where operations are only selected out of a very restricted number of gates, which are so-called Clifford gates. And it turns out that here, within this setting, you can realize generic states to some extent, with arbitrary entanglement, but with a very cheap computational cost, something that costs essentially polynomially with the system size. So it is clear that entanglement is not enough for complexity. Okay? And to some extent, it's not only enough, it's not informative. Okay? You can have how much entanglement as you want, but it could be that the state of matter that you are handling can be represented in a very simple manner, or in a manner which scales polynomially with a number of degrees of freedom in the system. So what are we missing? Okay? Now I'll try to picture it. This is a very simplified version of complexity of states phase diagram. I don't have any, let's say, rigorous way on this. Just take it as is. So we have one axis that we understand very well, is the lack of separability entanglement. And we know that here, everything is easy, whatever the other axis is, because we can use tensor network methods to represent our states. But then we also know that on this side, there can be both easy and hard task. Okay? Now, what we want to understand is what is in this axis. That's the goal. Okay? And in order to understand it, come back to the original question. Okay, we want to understand something that a quantum computer struggle with. So what is a quantum computer at the very end, at least for a theorist? We have a problem of interest, so something that we want to solve. There is some quantum algorithm, some pot, dangerous sorcery. Okay? And then, at the very end, what we need to realize on a device is a sequence of physical operations, gates. Okay? Now, what is the most popular way of doing that in a way which is correct, so which is error corrected, is utilize gates which are divided into two classes. One in this black box, a so-called Clifford gates. And you can recognize here there are local gates, like phase gate and Hadamard gate. And here there is something which is a gate which transfers or creates entanglement out of pairs of qubits. It's called C0. Okay? If you have never seen these matrices, don't worry about them. Just there is something on the black box. But then there is another box, which is orange. And this is a so-called T gate, which looks extremely innocent from a very body viewpoint. It's just a rotation of a Z around the z-axis. Okay? Very simple gate. Now it can be shown, and this is resolved by Bravi and Kitaev, that if you are able to realize all these four types of gates, you can have universal quantum computing. And this is, I would say, the overwhelming majority of quantum computing proposals, they are based on this kind of strategy. Okay? And now we want to understand why these classes, and let me say this. Okay, these are so-called Clifford. And it turns out that this class of states, if you have an error-corrected quantum computer, are easy. Okay? And if you're familiar with the toric code, all operations in the toric code which can be systematically error-corrected are Clifford operations. This actually is called a stabilizer code exactly for this reason. What is expensive is to realize gates of this type. Okay? And this is important because if you have only toric code operations, or Clifford operations, there is no quantum advantage actually. You can show that you can represent your states in a way which is efficiently classically simulatable. What you really need is as many of these as possible. Okay? So at the very end of the day, what makes the cost of a given computation, of a given quantum state, in a quantum computer meaningful is the number of T gates operation that you have to give to an experimentalist to realize the state. Yes?
It seems that you are not sharing your screen. There are quite a few people online. Okay. Sorry.
No worries, this is a major issue. Okay, sorry.
No, it does seem like you're sharing.
Yeah.
You can maybe stop and start again.
Yeah, I will do that.
Yeah.
I will do that. Can they see that now?
Yes.
Very good.
Ah, thank you.
I apologize.
No, it seems like it was just a little Zoom glitch because you were sharing.
No worries. Okay.
Thank you.
So the idea is that at the very first order we can see the amount of T gates needed for a computation is the dominant cost of computing. Okay. Now how you define these things more rigorously, this is magic. Given a target state, we want to see what is the magic of this is. This is, and you given an initial product state, which is not correlated and is not magical, like something which is all zero. Magic is the minimal amount of non-Clifford operation that you need to apply to this state to realize psi. Notice minimal. This is problematic. You have the same in entanglement. And that's why entanglement is very hard to measure and also to define in some cases for mixed states, for instance. So we want to quantify that. Now we have another axis for this phase diagram. Is this magic, also called no stabilizerness. And it is clear that we have states of matter here, low entangled, whatever magic we can simulate. But we also have states here which have a lot of entanglement, whatever entanglement, a little magic we can simulate. Actually, if you are interested in the method, this is called Pauli computing. There might be that method also in the middle. These are this Clifford augmented MPS. I will not talk about it. I think it's an interesting recent innovation. But what is clear is that if we want to have a state which is hard for a classical machine, we have to go in this corner. Okay. That's a kind of a complexity phase diagram. And now there are some questions that we can ask. Okay, we have a handle over complexity, so we can ask, is there a relation between the two axes? Are states of matter, for instance, realized by local Hamiltonians, constrained into the properties of magic and entanglement and mutual between them? Can we utilize magic to diagnose phases of matter? Okay? How this relate to physical phenomena? Okay? And is it fundamental for certain states? Okay, like we know that entanglement is fundamental for certain states. Is magic also fundamental? We don't know. Okay? And I would say that until 2 years ago, there was essentially nothing. There were maybe 2 papers addressing this. And now there is a flood of papers, especially since last year. And I will cite some of these, but I want to mention this is a very active field of research, not only in condensed matter, you know, there is also some particle physicists are also interested into this problem. Okay, before continuing and going to the meat, I want to show you a slide that, at least for me, when I understood it, made things much clearer. Okay? Which is a comparison between what entanglement and magic is in terms of resources. Okay? Here you can see two tables, okay, entanglement and magic, and here we have free states, free operation, resource, and the measure. So entanglement as a resource has free states, and the free states are separable states. Okay? States where the density matrix is perfectly separable, like product states. The free operation are OCC, and the resource that you want to compute in entanglement is how many entangled states are you giving to the circuit. Okay? Or if you want entangled states like C naughts. In addition, we also know how to measure it. For instance, for pure states, you can use the for normal entropy. Magic has a completely different table. So the free states are not separable. These are stabilizer states. So if you have in mind the toric code, any eigenstate of the toric code will be here, will be a free states in magic. What are the free operations? The free operations are this Clifford operation that I was mentioning earlier. So Hadamard, phase gate, C naught. And what is instead costly, so the resource, are states which are realized by this T-gate, this simple rotation of pi over 4 that I was mentioning earlier. Okay. That's kind of a table. If you're familiar with the resource theory of entanglement, that's just a parallel with this magic. Okay. So why shall we bother? This is also very, this is maybe important and complex. Why shall we bother at all? And I would like to give you 2 motivations. I mean, the first one for me is that whenever I heard the word complexity, it's clear that if you understand something along that direction, this opens space for new physics and can also open space for new computational methods. I mean, at the end, that's also what we're interested in. But there is also a second reason that is rather fundamental for experimental implications. Because if we compute this thing, or if we know something about this magic, this provides us a rigorous lower bound for any possible quantum computation that can be done in the future trying to represent the state. So this is really kind of a twofold motivation from my perspective. And okay, this is not only theory, I would like also to show this, the experimental side. This is an experiment done in the group of Misha Lukin at Harvard last year, where you utilize Rydberg atoms to do certain error-corrected things. I mean, it's not important what the details of the experiments are. The most important figure is, as always, or often in paper, is the last figure of the paper. And in this figure, they have 2 plots. One is an entanglement entropy, or any 2 entropy, plot as a function of subsystem size. And here, what they want to show with this figure is that they are able to realize states which have a lot of entanglement. But what they want to do at the very same time is to show something which is related to magic. It's called adaptive Bell magic, or additive Bell magic, which is also large. Okay? So this is important because it emphasizes that from an experimental point, it is fundamental to demonstrate that in your lab you are able to create both a lot of entanglement and a lot of magic to claim that you can do something that cannot be done on classical computers. Okay? So this is really important. And here the resources are Bell pairs and these are T states. Now, how do we compute this thing? Now, there are 2 problems that as many body theorists face. So the first is that, okay, it's a very nice concept, but at the end I have to do computation. Okay? What do I compute? And if you look at all the measures of magic until a few years ago, they always required a minimization, which is typically non-convex. So no way you're going to do a numerical simulation to compute this. And this is really the definition. Magic is the minimal amount of, whenever you hear the word minimal, problem. Okay? It's not going to be free lunch. But on top of this, for a very few things that don't have this minimization, we have no theoretical way of computing them. Okay? Of course, this is not a task I can answer. This I have to, I need help from my quantum information colleagues. But this is maybe a task that as many-body physicists we can try to answer. Okay? And in particular, okay, this is really the thing. There is no complex optimization. And in particular, what happened a few years ago is that Alio Sham and his group at Boston, they put forward this quantity, which is also called stabilizer Rayleigh entropy. And it turns out that this is a good measure of magic for pure states. So what is this? Given a state rho, you have something which is very similar to an entropy, but here you notice very well, instead of having the trace of rho or something else, you have the expectation value of an operator P, and this P is a collection of Pauli operators, so-called Pauli string. Okay. So if you want to measure this quantity, you just have to take the expectation value of all the possible Pauli strings in your state. First thing, when you see this, you are happy, because it's a formula, no minimization, I can compute it. Okay, if I have a state, I can compute it. After this first positive moment, there is a very degrading period. Is how many of these Pauli strings you have? Well, 4 Pauli matrices per site, and this is going to be 4 to the n. So measuring this stuff is harder than representing your state. Okay? So, doesn't smell good. Okay? Very nice, but this is very negative. However, what happens is that if you use certain kind of states that you postulate are the correct solution of your problem, and this in condenser matter we often consider a class of states which is called tensor networks, and I'm not going to assume that you know everything, just okay, this is a class of variational states. It turned out, this is a very beautiful result by Haug and Piroli, that you can compute this in something which is polynomial in the number of states. The problem is that these methods are extreme. I have to say, this is a really elegant observation. The problem is that in terms of doing concrete computations, this cost scales with a quantity chi, which for those of you in the known is the bond dimension. If you don't know, this is roughly the entanglement of a state, to the 6n, where n is the index of this Rényi entropy. Though this implies that the computations are very much limited by the fact that, that this cost blows up very fast. This is of course not the end of the story. There were people, so in particular displayed by Lamy and Kollura, that show that if you do sampling of a state, you can actually put down this cost greatly, okay? I mean, really making it computable, or something which scales like the entanglement or the bond dimension to the cube. And they indeed showed also some numerical simulation discussing quantum quenches in Ising model, where they were able to compute this magic for a long time scale. I think this is the first computation of magic over a quantum quench. However, it's hard to scale to 2D, to periodic systems. Typically, for this method, you have to consider only specific partitions, so there are still some limitations. So what we try to do before doing any physics is to develop some numerical methods to compute this stuff. And the first time, we did two things. One thing is actually I will not be talking about, is to write down the expectation values of this very complicated entropy, also as a tensor network, we call Pauli MPS, and then try to contract it. And it turned out that this method, so far, I would say, is the best in terms of between all those on the market in terms of practical experience. There's no sampling error. It's very controlled.
So this is not stochastic, sorry.
This is not stochastic at all.
So it's like the MRG. So
yes, I don't have to sample.
Okay.
I'm actually contracting a 2D transfer matrix. Okay, so this is, you can use all the knowledge from Condon transfer matrix, the normalization group there. And the scaling is modest, so it's chi to the 4th. We can do the simulations. Okay. But I want to tell you something else, which is based on merging somehow concepts from Monte Carlo and then implementing them in tensor networks. I'm sorry, the next few slides they will be more methodological, but these are really needed in order to then make eventual statements about physical problems. Okay? And the idea that we had is extremely naive. Okay? Whenever you have something written like this, you notice this is positive definite, this is power 2. What I can do, I can try to sample this. It's a distribution. I can try to sample this. And what is a distribution is not a conventional distribution that we have in partition function. It's a distribution in the Pauli space. So this is why we call it Pauli Markov chain. So in a Markov chain that moves from Pauli operator to another Pauli operator. Okay? And the algorithm is essentially like a conventional Monte Carlo. The only thing is that the Markov chain is slightly different. And now, this algorithm you can in principle apply to everything. Either you have a wave function from exact diagonalization, you have a variational wave function, you have an experiment to some extent, or you have a tensor network. And that's what we did. We formulated this in the context of a particular type of tensor network, which is called 3. Just for practical reason, you can do that with PEPs. Actually, we've done with PEPs, with MPS and other things. So conceptually, everything follows. The advantage of 3 is that certain type of contractions are extremely practical, so you don't have any scaling with the volume. Whenever you see log n, this implies that this method costs the same in 1D, 2D, and 3D. So as long as you can write the tensor network correctly, there is no cost in directionality. You don't want me to go over this, okay? It's magic. This is an extra level of magic. I will not say anything about it. I want to, however, emphasize that whenever you have methods that do a Markov chain, you always have an hidden problem under the carpet, which is autocorrelations. Because it could be that you have a beautiful algorithm, but then you turn it in practice, your chain is never Markov. You have to compute autocorrelation times. And this is just a plot to show you. I mean, that's the autocorrelation time of this Pauli Markov chain as a function of volume for 2Ds in gauge theory, but for a model. Okay? Don't care. If this grows very fast, the simulation becomes very expensive. If this plateaus, the simulation is equally costly for any system size from this viewpoint. And it turns out that this, for all the models that we'll be looking at, typically most of these stabilizer Rayleigh entropies, magic measures, they do not have any autocorrelation. We don't know why, it's just numerical evidence. But this implies that this algorithm can be utilized to make non-trivial simulations. Okay. So let me summarize shortly this part. I mean, now I think we have methods, at least in the context of tensor network, maybe even beyond, that allow us to do trustworthy computations, so computation where you can put error bars for relatively large volumes, and states which are also entangled, okay, or at least some entanglement. Now we can do some physics. Okay? So far, zero physics, zero observations, zero predictions. Now we do some physics. So before starting working into models, I would like to show you what is the relation between entanglement and magic. I mean, maybe a prior. There are states in quantum information that have zero magic and a lot of entanglement, these Clifford circuits. But there are also the opposite, states which have zero entanglement and a lot of magic. Okay? So it is clear that a direct relation between magic and entanglement cannot exist. Okay? We have to restrict ourselves to classes of states which have some physical meaning and try to understand whether in that class a correlation exists. And what we did that in the context of matrix product states of this tensor network. This is really work mostly done by Martina. We studied the phase diagram of some Hamiltonian. It's a spin-1 Heisenberg model with single line anisotropy. It's not important, okay? In fact, other models, they show the same thing. And here what I'm showing, in the plot on the left, I'm showing the magic of the state as a function of the bond dimension. And here I'm showing the entanglement entropy as a function of bond dimension. Caveat. These bond dimensions are ridiculously low. Ridiculously low. I will show you in the next slide why. And these are done at 3 different classes of critical points. And one can notice already about bare eye is that typically this magic seems to attain a constant value, so seems to converge much faster than entanglement. And this is not only a visual thing. Check the scale. I mean, here fluctuations are awarded a % at this level. While here, if you want fluctuation at the % level, you need a considerably large bond dimension. Okay? So there is something going on here. Okay? And what we analyzed in more detail is the scaling of this object. And for in the gapped phases, we couldn't even do a scaling because magic was converging so fast to correct value that it was impossible to say anything. So we could say only something for critical points by using very small bond dimension because convergence was very fast. And the convergence has this form. And we were extremely surprised because if you know how entanglement scale is MPS, this is not as good. This should be much worse. Depends also a bit on the model, by the way. Okay? And at the same time, there was an analytical computation for random MPS that also showed the same results. I don't know if the two results are related. But this is just to emphasize that if you look at states, which are ground states of local Hamiltonians, at least in one dimension, magic and entanglement are probably not disconnected, but they are connected in some form. And it turns out that you can utilize this to design better computational methods. And I want to emphasize a work not done by us, which I find extremely interesting, where these colleagues, they augmented MPS with random Clifford, with structured Clifford, sorry, and they reach much better results than with conventional MPS. I find this very interesting. Okay, but this is really due to the fact that MPS have a lot of magic that they convert very fast. Now, that's one type of understanding, then you can also go a bit deeper. Just not look at entropies or scaling, just try to understand if there is an exact relationship between magic and entanglement. And it turns out that this is a trivial observation. If you look at states which are stabilizers, and you look at their entanglement spectrum, which is defined as follows: I take the state, I divide it into two parts, I look at the reduced density matrix rho A by tracing B out, and I look at the eigenvalues. If you have a stabilizer states, the entanglement spectrum is like this. So there is a finite number of states which have a finite value, lambda k, and then the rest is zero. That's so-called flat entanglement spectrum. Okay? That looks interesting. Maybe all states which have no magic have flat entanglement spectrum. It's not so true. Okay? It turns out that stabilizer states have flat entanglement spectrum, but the opposite is not true. Even product states can have magic. So this is apparently problematic, but what we did with our quantum information colleagues, Alyosha and so on and so forth, is that you can utilize the concept of a Clifford orbit. So instead of having just a state, what I do, I take this state, and then I start applying Clifford operations. If I apply a Clifford operation to a stabilizer, it will stay stabilizer. If instead I apply it to a state which is not stabilizer, it will make a mess. And you can quantify this mess analytically with a theorem, and essentially what happens is that if you do a Clifford orbit, the average of this flatness in the entanglement spectrum, up to some numerical factors that depend on the Hilbert space dimension, blah, 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 is related exactly to magic. So the more rough an entanglement spectrum over evolution is, the more magic a state has, which was somehow very surprising to us, okay? That you can do it really in terms of a theorem. Good. So, what we have learned so far, already something different. We have this method to compute the magic, and we can make some statements. Magic for MPS is related to entanglement in some form. And in addition, magic overall, even beyond MPS, is related to properties of the entanglement spectrum in an exact manner. Now, can we make some predictions now about physical phenomena? Okay. And for this, I will show you three examples depending on time, which I'm not so sure I'm doing. The first one is about critical states of matter, so it's a conformal field theory. Then I will move to Z2 gauge theory, and then I will show you slightly more complicated gauge theory. Okay? So the thing that we did once we had these tensor networks available is that, okay, let's try to check what happens if I have a state and where is this magic larger? Because we know that if we have critical states, entanglement is large, if at least in one dimension, and if you have non-critical state, entanglement is small. So does magic follow the same pattern or not? So, and these are some results that we got for the three-state clock model. Okay. This model has a phase transition for this parameter h around 1. And here you have magic plotted as a function of h for different volumes, from L equal to 8 to 128. And already by visual inspection, you seems to be that there is a peak here, and you can utilize conventional finite size scaling theory, and it looks like magic is indeed following some sort of universal scaling behavior with a maximum at the critical point. Good. So this is somehow similar to entanglement. Magic peaks at the critical point. But then you say, okay, let me try another model. I mean, by the way, let me mention, magic is not like entanglement entropy that you can compute it easily in conformal field theory with a replica. If you're familiar with that, it's as difficult as computing Shannon entropies with a replica, which is known to be highly non-trivial task, okay? Or non-trivial task. And this is the result for another model. It's actually the same single ion anisotropy spin chain that I had before, which has two-phase transition denoted by these dashed lines. And this is the magic computed as a function of different volumes from 8 to 128. And here, you see nothing. Okay? Magic at some point a maximum. The maximum is actually inside the phase. It's completely unrelated to.
What is the horizontal axis?
The horizontal axis in this model is so-called single ion anisotropy.
Okay.
So there will be an aldane phase. This is a large D phase, and this is an antiferromagnet.
Okay.
Yeah? But if you do a scan in another direction, you observe the same thing. That magic is I mean, if you look at the full state magic, is completely uninformative about the transition. And let me mention that these are results by Claudio Castelnuovo, Poeti Trabuga, in the context of Rocha-Kivelson type wave function that arrive at the same conclusion. If you look at the magic of the full state, it doesn't get the phase transition right. Okay? Then what we said, okay, we can do the same trick that people have done, Casini Huerta, for instance, and try to define not the magic of a state, but the mutual magic between two parts of the system, like a mutual information. Of course, now I'm abusing language because these M2 are not measures of magic for mixed states, so I'm not gonna have a rigorous measure. This is more checking how non-stabilizer any entropy behaves. Okay, so maybe the word long-range magic is not justified. That's the same plot that we had before, where we saw nothing, and this instead, this new quantity, this mutual magic, as a function of the same parameter d. And here you see something which is very different. Close to the transition point, this quantity is now exhibiting either peaks or anti-peaks. Okay? So there is a sense in which we can now define, we can now observe criticality as something where, in terms of magic, we cannot separate points at distance. Okay? You cannot have a simple, if you want, you cannot have a simple circuit that reproduces the density matrix of two distance chunk of vector. Okay? This essentially, the reason why we believe it works is because this cleans all non-universal contributions that instead the full state magic has, like also the entanglement entropy has. And this, for all the models that we have studied, always displays peak at critical points.
But here
Never fails.
Your maxima is not at 1. It's
This
somewhere
one?
Yeah, somewhere
Okay,
below.
no. The reason is that you cannot see it at 1. If you zoom around it, I mean, at any fixed system size, it is not at 1. But if you zoom around it, to the extent that we can actually control our error bars, which is non-trivial, the maximum moves towards 1. We cannot correct, I mean, if you are asking me whether we can precisely position the critical point here, I will tell you not with this computation. We will have to use the Pauli MTS, which is more potent. So the sum up is that, okay, this is interesting. For conformal theory in one dimension, so for simple critical theories, magic displays universal features. We can even do Frank scaling in certain cases. But it's important to take it with a caveat. This is only working when we consider the proper quantities which have to be defined as this kind of long-range magic. Now, the second step that got my attention is, well, fine, but 1 plus 1 dimension is maybe too simple. Why don't we look at gauge theories? Okay? And the reason actually was stimulated by a talk given by Jesse Stryker at the energy physics workshop last year, when he showed this table, which is taken from this very nice paper with Doré. And essentially what these guys are doing, these are lattice QCD people, that they want to simulate gauge theories on large lattices. And since a few years, there has been interest in trying to do that, or trying to understand whether this can be done in a quantum computer. Okay, that's their interest. And so the way they quantify complexity is counting the number of T-gates. Okay, counting the magic. Of course, they don't do it by computing the magic of a state because they didn't know how to do it. They do it by taking a state and trying to write down a circuit which has the minimum number of T. And this is a very relatively simple model. It's a 2-dimensional SU2 gauge theory, 1 plus 1 dimension, and the task is state preparation. The volumes are like 100, 2,000 sites. But then you look at the last column. Okay, I'm not so sure if you clearly see the exponents, but I can read it off for you. This is 10 to the 15. Guys, when you see 10 to the 15 in physics, it's collider physics to me. Okay? Does not exist. It's something I don't understand. Let me say like this. Okay? I mean, of course, if that's the resource needed for a quantum computer to realize these states, even if the quantum computer works at the gigahertz level, there is no way we can solve anything. It's also a very simple theory. Okay? Something that we can simulate in
How
few
do they
minutes.
count this? How do they count 10 to the power 50?
Yes, they do it like this. Ah, no. You want to know how they get this
You
number
say they
exactly?
count
This is
it.
an estimate. It's an estimate. No, of course, you can't store this number. Okay? It's an estimate. It's very well controlled, however. I mean, there is nothing sloppy in this paper. I want to make it very clear. It's a very rigorous study. But I think this is one of the messages of this paper. I mean, we have to be careful. I mean, first, the number of qubits is large, but 20,000, to me, it's not so large. I mean, at the end, you want to simulate 1,000 sites. It's a gauge theory, so the local Hilbert space is huge. So it's clear that you need a lot of qubits. But the point is that even if you have the qubits and they do work perfectly, perfectly, error corrected and so on and so forth. Just don't have time. I mean, of course, these are upper bounds. Huh? So our question was, can we actually provide rigorous lower bounds that let us understand whether this is an amazing overshoot or whether there are more reasonable estimates we can make. Okay. Now, the first thing we did, maybe more compressed matter expired, we tried with a simple three-dimensional gauge, so 2 plus 1 dimensional gauge theory is a Z2 gauge theory, because it's also the toric code. Okay, so many reasons why this is interesting. Essentially, it's a model on the square lattice where you have plaquette terms and then local terms that want to pin Z configurations. And the model has a phase diagram as a function of this value of H, where here there is a paramagnetic phase, and here when this H dominates, there is a phase which we call topological, so it's a Z2 spin liquid. And in this plot here, what you see is the magic as a function of this value of H for different volumes, for linear volumes, linear dimension of our square. And what you can see is that this is very different from 1D. Here, magic does not pick at the transition point, it's a full state magic. Actually, it shows a crossing. And what is somehow remarkable is that this crossing, if you try to do a finite size effect, finite size scaling, gives you almost amazing collapse. Okay? So it implies that magic has a lot of universal content in these gauge theories. And what is even, oh sorry, this is not the spin liquid, it's a para. Okay, so they are inverted. And what is even more amazing is that we say it's impossible that magic get the transition point like better than a percent level from these small volumes. I mean, these are 60 spins. And then we say, okay, let's try the Binder cumulant and see how it works. And then we computed the Binder cumulant. The Binder cumulant at these volumes, this is a Binder cumulant of Wilson loop, is rubbish. So, very surprisingly, magic is much better at finite point dimension and so on and so forth, at detecting the transition point, than the best thing we can think of, which is the order parameter. Okay? So it looks like there is something that we clearly do not understand here. Okay?
The mu and nu the slide before is exactly the same critical exponents for the easing element.
For the correlation, yes, it is exactly the same. In fact, what you can show is that the magic of the Z2 gauge theory is exactly the magic of the Ising model after duality, because the duality transformation in this particular theory is actually a Clifford transformation, so you cannot change it. And it turns out nu is also exactly the same exponent. I forgot the number. Okay? Gamma, I don't know. Gamma, I will have to check. So we say, okay, fine, but this is not a theory which will enter any discussion with an energy physicist. Okay, there are no fermions, so almost by definition, it's not something that will click. So then we say, okay, let's try a theory which clicks. And the theory is a U1 gauge theory, including staggered fermions. We didn't use the conventional Wilson formulation. We use a spin model formulation, which is so-called Pendley-Sachs-Seguta model, which is an interesting model in the context of spin system, where also Frederic has contributed to determine the phase diagram of. And this has also been realized in the experiment, but it's exactly dual to a gauge theory. If you are interested in how this duality happens, I can give you more details. And what is interesting in this model is there's a phase diagram, which is pretty rich. Oh, sorry, I'm missing up the notation now. So here this V is actually the next nearest neighbor interaction of this type. Nearest neighbor interaction is infinite. And this U is this delta, and this omega is fixed to 1. Okay? Sorry for mishandling of notation. And this model has different phases. There is a Z3 phase, where there is 1 spin up and 2 spin down, 1 spin up and 2 spin down, and so on and so forth. Then there is a more conventional Z2 phase, which is just up, down, up, down, up, down, up, down. And then there is a bunch of paramagnetic states. Here is a single paramagnetic phase. Luckily, there are 2 exactly soluble ones, this red one and the red one. And then there is also an RK line, which is solvable analytically, is this black one. And what you see here in this plot is the magic of this state, of the ground state of the theory at different points in space, computed on a relatively small volume, 30 sites. And what one can see is that in the ordered phases, there is a very small magic because they're ordered along Z, so they're almost stabilizers. And then the magic seems to start increasing, and there are almost local, not peaks of magic, but very, very fast changes close to the transition lines, which is following exactly the maximum, exactly this kind of brown lines here. Okay. There is something which is even more interesting, is that magic is the largest in the phase that we don't care about. Okay? Which is somehow paradoxically. So realizing a paramagnet would be much more costly than, at least from this plot, than analyzing interesting phases. And what we need? We did some cuts along this phase diagram, which features different type of transition. This is a called Potts transition. That's a tricritical easing transition, and these are two transition, either easing. This is easing, and this other one is actually probably. So this is this value of V. I think I wouldn't know what this transition is. It's probably chiral. Okay. And what we found is that if we look at the magic of the state, it does something, but it's not so clear what it does. Typically, it peaks inside phases. Okay. However, if we look at the derivative with respect to parameters, either u or v, we always see peaks close to transition points. So this implies that magic gets the physics because it peaks, its derivative peaks at the transition point. However, the absolute value of magic is not particularly important. Okay, it can be large or not. And why are critical points of this model or equivalent of gauge theory is important? Because if you're interested in at some point answering questions in gauge theories, you will have to approach what's called continuum limit, so critical points. So this is kind of giving us some hope that this can be done, because typically at critical points, resources that the quantum computer will need are definitely not maximal. Okay? So this was a kind of relatively good message. Okay, what we have learned so far, we can compute magic. It is related to entanglement, at least in some specific cases, albeit not trivially. And it seems to relate to physical phenomena. And I have given you two examples, conformal field theories and lattice gauge theory. Of course, I mean, have I really answered the question that I posed at the beginning? Well, kind of no. Okay, I tried. Okay, I said something. I mean, what is clear from our results is that even for the simple type of models that we are looking at, realizing them in an error-corrected quantum computer is not going to be cheap. Okay? You will need an extensive amount of T-gates, minimum, to realize those. At least now we have rigorous lower bounds to do this. Maybe what we can learn out of this is that we can utilize the fact that we now understand how these quantum resources are spread over a physical system to design better algorithms, okay, which was for sure not possible before. Okay? And there are now plenty of open questions. I mean, how does magic and entanglement relate to in real-time dynamics, which is something I've not talked about. Okay, and I think there are some works now in the context of random quantum circuits where there seems to be interesting, the equivalent of measurement-induced transition now with magic. Can we use that for get better computational methods, either for magic or based on magic? I think there are many people working on this. Are there other relations to physical phenomena? And of course, we are interested in this in condensed matter, but there have been also works in both nuclear physics and particle theory, trying to understand whether magic plays any role in the physical phenomena these colleagues are interested in. And ultimately, at the very broad level, can we really get a more complete understanding of where quantum simulation is really beyond classical computing? Okay? This, I think, is an open quest, but we shall keep going after it. Okay, with that, I would like to thank the people. Let me emphasize poetry, Martina, Emanuele, and Pedro, which did most of these computations, and thank you for your attention.
Thank you very much, Marcello. It's over to you. Questions, Richard?
I have two small methodological questions. The first one is all this is possible in the tensor network structure because you can sample these Pauli strings exactly, right? So if you have a mathematical representation like a neural network state that is not or another. I'm not saying it must be that one. So if I have a it's not the task of sampling from that distribution is not treatable, right?
It's not trivial, but I think people are thinking about this. I mean, on neural network, probably you should ask the person just right behind you. I can tell you in the context of quantum Monte Carlo.
Yes.
There, people start to have some answers. There is a recent work by Brian Clark that studies that in the context of essentially sampling directly the partition function work, written as a tensor, with a sort of SSE sampling. And there it works. They can really sample only certain type of destabilizer oriented, but they can do that.
And what do you use as, I mean, for the important sampling? I would like to comment about the probabilities that you use for the important sampling. What do you?
What we use?
Yes.
Oh, okay. No, we use just the trace of rho p.
Ah, okay. So
Yeah. No, it's very simple. But of course, you can also use higher powers. What we have observed, is also surprising, is that for higher powers, the autocorrelation time is the same at trace of rho p fourth power, which is the lowest that you take, which is not something clear to me, because of course you have changed the probability distribution, so autocorrelation should change. But okay.
Yeah. I have a question regarding kind of extensivity or something. You showed magic, and sometimes they are of 4 to 0.4, but then also.
Oh, this is the density of magic. Sorry.
It's density of magic.
Yes.
Okay, so it's extensive, like.
It's always extensive. Yes.
Okay, well, that was not clear. But then on the peak of the phase transition, if it has a peak, is it actually divergent? Because I mean the feature does not seem very clear. If
Which one? This one?
yeah, or also others.
Okay. Whether there is a true divergence, we cannot say.
It
Of
could also
course.
be that gamma kind of is zero or something.
Yes, it could be that. Well, the point is we see a finite gamma when we do the finite size scaling. But of course, it could be that at some point, gamma saturates. Okay, so we essentially are observing anomalous scaling at finite volume, and then at some point there will be kind of a. However, I mean, I'm not so sure. Okay, because in principle it could be that magic is discontinuous at the critical point. Because if I think about a resource, I mean, at some point he has to see that the volume is finite, right? So essentially, will be the resource. If the correlation length is finite, will be just the sum of resources. So we'll approach a constant, and instead, if this correlation cannot be, if this partitioning cannot be done, this stuff explodes. Okay. I think based on our numerics, we cannot conclusively say that. Also because we don't have a theory. I mean, we don't have a field theory for that, which is a bit problematic to make a statement of this type. Now we can access larger system size than this with this Pauli MPS, but it's not outrageously large. Okay, maybe we can do 1,000 sites, but no more. So, and for this problem, I think this will not be enough.
Thank you.
Cheers.
Can I ask a very stupid question? I have a pure singlet on a two sides. So two side
Yes.
pure singlet. What's the magic?
Zero. Because
For
it's
up,
a bad pair.
If it's up,
No, if it's up, it's not a singlet. Ah, okay, sorry.
I'm just trying to understand like what would be the quantity for two spins.
Okay. If you want a lot of magic, you put two spins this way. No way you can realize it with a Clifford circuit. It's a rotation out of plane, because essentially Clifford circuit, they move you only on the poles of the block sphere, right? And so this is treated as some magic. If I have a singlet, by definition, you know that these have exactly zero magic. The reason is the following. How do you realize this? Well, you take a product state, C naught plus Adamant.
Yeah.
This is a Clifford circle. So, yes.
But aren't you a bit bothered if a product state has a lot of magic?
No, this is not a contradiction. No, I'm not bothered at all. I have a resource theory, and I determine what is cheap and what is not. Okay? And now you can tell me, okay, but is this magic really quantum mechanical?
I didn't ask that, but I'm.
No, but let me ask you. Let me ask you, okay? Okay, how are Bell inequalities probed? So if I have a state like this, how do I probe that this violates Bell inequality? Very basic quantum mechanics now. How do I probe it? I need to decide the basis where I measure it, right? Well, if you decide any Pauli basis, you're not going to evaluate Bell inequalities. You know this?
You need 120 degrees.
Bad. Exactly. So this implies that even if you have entanglement, if you are just measuring in Pauli basis and you are being extremely naive, you need to put magic in your measurement apparatus to demonstrate violation of Bell inequality. This should tell you immediately that this is serious. Okay? If I could violate Bell inequalities with just a state with zero magic, I would say, okay, then I will be concerned. Okay? What does it mean? I can have the maximum, I mean, you know, guys, there is a pyramid of quantum correlations. Discord, steering, many, and then there is Bell. Well, if I can have the top correlation without magic, this magic is probably not so fundamental. But the reality, from this simple example, at least, this is incorrect. Yes?
I think that it is just that we are used to think of entanglement as the difficult thing, and therefore it's surprising that the separable state may have magic. But if you look at it from the point of view of stabilizer states, it's exactly the same viewpoint. Stabilizer states are highly entangled, but they are triggered. So if Tarzan had been educated by monkeys to only work with magic, it would ask the same question but the other way around. So
I agree. But to be frank, this is a problem that I also had to face at the beginning.
I know.
Because you see this, okay, that's complex. But then let me turn this by 40 degrees and then actually I can turn it also a bit, and it's already much less trivial than this. Okay? But then when you see this bell pair example, I think that's serious.
For a like a magic of a subregion in a CFT, do you know how it would scale with the size of subregion?
If you want a formula, we don't have it. Okay? What we observe is that typically it scales linearly. Actually, not the magic, we don't know. We know the stabilizer Renyi entropy. This scales linearly with the length of the region. Okay? It could be that there is a logarithmic correction to it. The problem, that's the problem of the stabilizer Renyi entropy, is that it's really a measure of magic only under certain conditions. So what we can do, we can compute another thing which is called, which poetry has introduced in one of her papers, which is called mana entropy. Star entropy. It looks like I'm playing Dungeons and Dragons now. Okay. So this mana entropy, this is a good measure of magic, and this we can now compute in conformal field theories on the lattice set, of course. And there we are observing linear, very likely with a log correction. But there is no theorem that or field theory prediction for this.
There's a question on Zoom. Is there an intuitive picture why the magic has features close to critical points?
No. No. I think we don't have an intuition. Because we cannot compute it. So, I speak to the camera? Okay. We cannot compute it analytically in any case. So it's very hard to build an intuition of why there is a divergence. I mean, of course, you can say because correlation functions of the other parameter are inside the Pauli string, but they are a measure of zero in the Pauli string, so this is not an explanation to me.
Maybe I will ask one question. Did I get it right that states which have a large magic are will be better probed with quantum computers? So quantum computers would be...
quantum computer will struggle. I mean, first, if you have a lot of magic and a lot of entanglement, you are pretty much ensured that classical methods they don't like this, okay? Because you don't have any simple classical method. But also the quantum computer, for it will not be so cheap. Because you will need a lot of operations, so the time scale of the quantum computer will blow up. So it's not a fundamental issue, but it's a practical issue.
So entanglement entropies are for a pure state. Entanglement entropy is an entanglement monotone, so you can use it as a measure of entanglement, but not for a mixed state.
Yes.
What about the stabilizer Renyi entropy? Is it a monotone also for mixed states?
No, it is not. It is not. It's not even faithful for mixed states. So you can have mixed states which have zero magic but have finite entanglement stabilizer Renyi entropy. So for mixed states, you have to look at different quantities. I can tell you which ones.
Okay, but in this case, how are you going to measure your measurement-induced magic transition?
No, there we look at the evolution of trajectories, so they're always pure states.
Okay.
In that case,
okay, so you look at, so it has the same property as entanglement that doesn't. Entanglement entropy doesn't average, so it's a nonlinear function of the status, so it doesn't average the density matrix. Correct?
Exactly.
And the same is for magic. Okay.
Correct.
I think in one slide you mentioned something like Clifford amended MPS or something.
Yes.
you said that this is promising, or I don't know. You just said it's
Yeah.
working pretty good.
Mm-hmm.
Can you say for what exact task?
Mm-hmm.
And because like these are kind of like seems like orthogonal, like the methods that we know that work for Clifford, like stabilizer methods and NPS methods, they don't at least
They don't talk to
on
each
the
other.
side. So, yeah, exactly. Like how
You're
does
perfectly
that
right.
work?
So let me tell you in 20 seconds how it works. Essentially, what you are doing there, you have your MPO, which can be a Hamiltonian search on top of an MPS. And what you start doing, you put here disentanglers, okay? Which is something that people have always done in quantum. If you think about Mera, it's full of disentanglers. So essentially, you are changing the structure of your variational state. But you do it in such a manner that these disentanglers are only taken from the Clifford group. If you do that, and your Hamiltonian can be written as a sum of Pauli operations, it is straightforward to actually include them in the Hamiltonian, not in the state. So at same bond dimension, you can represent a state which has larger entanglement. This is really, I mean, how much large, then you have to determine, is going to be problem dependent, but this seems to be, I mean, a huge gain, because essentially the only thing you have to do a minimization here, so something which does not scale with system size, just a factor, but you gain in entanglement. So I find this a very nice idea. I'm not part of it, so.
On similar spirit with the question from you, which was about the bulk of the CFT or the number of particles in the R. In similar spirit with the previous question, for entanglement on these graph tensor networks or even MPS, there's area and volume laws depending on where you place your boundary, more or less. So for magic, of course, there is not right now, but do you think it would, do you think such directions can exist for magic?
It could be. But for our experience, in all these cases that we have studied so far, and also other people, for ground states, magic is always extensive. It could be that there are, I think the question has to be formulated with this mutual magic. This is not going to be extensive, and this can be much more sensitive to critical behavior, maybe even topology, and so on and so forth. But the full state magic, I doubt that will lead to any classification.
There is another question on Zoom. Is magic also definable in the Heisenberg picture without any notion of quantum states?
What does it mean? Okay. Sorry, what?
Repeat the question.
Can you repeat?
Yeah, no, I have not. I forgot it already. Sorry. Does magic exist in the Heisenberg? Can you define magic in the Heisenberg picture?
I can explain the question.
Okay.
So you've got these classification methods that work in the Schrodinger picture. So you start with stabilizer state, it ends up in stabilizer state. But you can also work backwards in the Heisenberg picture. So if you start with a Pauli, if you just apply Cliffords, it's going to become other Paulis. But if you apply non-Clifford, it splits.
Yes.
So we are interested in doing Pauli propagation in the Heisenberg picture. And there is a sense that somehow magic is what makes these simulations hard. Or non-cliffordness is definitely what makes these simulations hard. But we don't have measures that we know about in this picture. So we want measures that work in the Heisenberg picture for non-cliffordness.
So you want the magic of an operator?
Exactly.
Okay. Stabilizer, they will only work if you have Q treats. Okay, there it will work, because they can map into this mana entropy. For spin 1/2, you will have to use robustness of magic, which is much harder to measure, but you could do it.
What's the robustness of magic?
Robustness of magic is a quantity. It requires also minimization, similar to robustness of entanglement.
Okay.
I can give you the references. And of course, if you do brute force, you can maybe do 3 or 4 spins. But there is an algorithm by Yoshioka and co-workers where they can maybe do 10 spins. But in general, it's hard. So this task that you're asking me, the answer is yes, but it's not trivial.
We can also chat about this more.
Okay. Sure.
Well, we had already a lot of questions. It seems that there are no more questions. So thank you very much again, Marcello.
Thank you.